It's a pleasure to meet with you all and give a talk. I only wish I could have done so in person, but someday down the line maybe. And before I get started, let me just please, I know this is dangerous, but I really do want to encourage you to interrupt me as much as you feel like, to ask questions, just to keep these virtual seminars, as lively as possible, and break the feeling like I'm talking to the wall in my office. So really feel free to interrupt me. And indeed, as Gyöngy said, this is there is a mean field element here, but there's no game theory. But there will be a mean field connection. But otherwise, this is a fairly new topic for me that I was told about by Scott Robertson and Casper Larson several years ago, and I should thank them for not really warning me about how intractable this problem is. But nonetheless, I was fortunate to have the courage, therefore, to work on it for a while, and we did make some progress. So I want to share with you our modest progress we made on this fascinating open problem. But more importantly, I hope you'll walk away from this talk feeling intrigued by this problem, which is really almost wide open. This is a kind of fascinating problem in my mind that there's been very little progress on. So I hope you'll agree. So this comes up in finance in the context of what are called stochastic local volatility models, where you try to take a local vol model and inject a stochastic vol term inside of it and calibrate this thing to market data. But mathematically, you can view the problem as inverting the Markovian projection. So I want to start by explaining what the Markovian projection is. And I'm guessing many of you have seen this before, but to get us all on the same page and warm up a bit, I'll state this theorem carefully. And to those of you who haven't seen this before, I'm honored to share with you this beautiful theorem. This is due to Gyöngy. Apologies, because I don't know how to pronounce this properly. And there's a more recent beautiful paper of Brunick-Shreve that extends this theorem in a number of directions. And the basic setup is as follows. So you start with some Ito process in any dimension, but I'll write the one-dimensional case since that's all we'll need. So B and sigma are just some generic progressively measurable processes living in some filtration with respect to which W is a Brownian motion. All we require is that these processes have some modest integrability. And the idea is that this drift and volatility can contain all kinds of additional randomness beyond the Brownian motion or even the XT process itself. And we want to project away all that additional randomness and end up with a Markovian SDE instead of a generic Ito process. And the Markovian projection, this theorem lets us do this. And the way we do this, we define two functions. As projection might lead you to suspect, there's a conditional expectation here. We take this drift and condition on the value of xt. And for the sigma, we do the same thing, but at the level of the square. Take the conditional expectation of sigma t squared given xt, and then take a square root outside. So one of the first conclusion of the theorem is that you can do this in a jointly measurable way. You can construct versions of these conditional expectations that are jointly measurable. So don't worry about that point. But the real conclusion of the theorem is that there exists a weak solution of the Markovian stochastic differential equation driven by these two functions b hat and sigma hat. So there exists, I'll call it x hat, solving this Markovian SDE. Where we use b hat of t xt as the drift and sigma hat of t xt as the volatility. And now there's no extra randomness here. This is a Markovian SDE, and we're saying there exists a weak solution of this equation such that actually, moreover, and this is the important part, the time t marginals agree with the original process. Okay, so this means equal in distribution. Okay, so a couple notable things here. First of all, when we take these conditional expectations, it's hard to really ensure anything about the regularity or niceness of these functions b hat and sigma hat. They're measurable. There's some integrability that comes from this assumption and Jensen's inequality, but otherwise, we're not going to have continuity in general, except under very strange assumptions. So the existence or uniqueness for this SDE are not clear a priori, and indeed uniqueness fails in general. So we can't assert necessarily that this is a genuine Markov process unless we know this SDE is well posed, but it's still a Markovian SDE in the sense that the coefficients just depend on t and xt and not any additional randomness. And the arguably more important part of the theorem is that we can do this in such a way that we preserve all of the time t marginals of the process. And the reason this is important in financial application and why this theorem has found a lot of financial application is that if we're thinking in terms of European option prices, if x and x hat are two different asset price models, then they induce all of the same European option prices. So this means in particular the expectation f of xt is the same as the expectation of f of x hat t for all reasonable functions f and for all times t. Okay, so there are several consequences of this in volatility modeling in finance, which I want to turn to next. But first, because I can't resist, I do want to sketch a nice, easy, modern proof of this theorem. Let me stress this is a sketch, of course. So I think the easiest way to see this is to take a test function, say phi of xt, apply Ito's formula, and take expectations, and you'll end up with the usual thing here. So you'll have bt times phi prime of xt half sigma squared times the second derivative of phi of xt. And then inside this expectation, you can condition on xt. You can use the Tower property. And the bt and sigma squared become their hat counterparts. Okay, and then if you stare at this for a minute, and let's say you define mu t to be the law of xt, then you will see after a moment's reflection that this mu t satisfies in a weak sense the Kolmogorov-Forward equation, or Fokker-Planck equation, associated with this hat SDE. So you could say the derivative of mu t integrating this function phi is given by mu t and then b hat phi prime half sigma half squared phi double prime. So if we have a solution of the Kolmogorov-Forward equation, it suggests to us that there should be a solution of the SDE that has those same time marginals. And indeed, recent results on what are called superposition principles due to Figali and more recently Trevisan ensure that if you have a solution of the Fokker-Planck equation associated to an SDE, and even knowing nothing about regularity or uniqueness of the equation, you can construct a solution of the SDE that has these given time marginals. So once you know that these time marginals satisfy this PDE, you can construct some solution of the SDE with these coefficients that has these same time marginals. So this is one way to see this using this recent machinery that was, I'll stress, not available when these things were originally proven. So this is the Markovian projection and a proof sketch, and the rest of the talk is about a way of inverting this, which I want to motivate first by discussing a bit about volatility modeling. But again, let me pause for a moment to encourage you to interrupt if there are any questions whatsoever so far. Happy to clarify anything. Okay. Otherwise, then let me do a super quick crash course on the highlights of volatility modeling from the past few decades from the perspective of this talk. So there's, of course, the Black-Scholes model, where things began, which models a stock price just as a geometric Brownian motion, which, of course, as we know now, has many shortcomings, and a follow-up, a more general framework that's become quite popular over the years is called the class of local volatility models, where you allow the sigma to depend in some general way on the stock price itself and the time, but on no additional randomness. So it's local in the sense that the volatility depends just locally on the current time and current value of the asset, not on any other external stochastic factors. One reason these models have been very popular is that in principle they can be calibrated exactly, I'm putting exactly in quotes, I'll clarify in a moment, using Dupier's formula. Which tells us that basically if we know a sufficiently rich family of option prices, specifically call options, so if we have access to market data on the call prices for every possible maturity and every possible strike, then we can deduce from this what the time marginals of the asset price should be, and that will uniquely determine what the sigma should be. So the sigma hat is determined essentially by this continuum of call option prices on the market. Now, of course, in practice, we don't have access to a continuum of prices. We don't have access to all of the maturities. So you have to think carefully about interpolating between the ones you're missing, and that is an important part of this calibration problem that I'm not going to talk about at all. But in theory, if you know the continuum, this is why I say exactly, because you need to really know, unrealistically know that you have access to the full spectrum of option prices here. But ignoring that point, in principle, you can exactly calibrate a local volatility model using Dupier's formula. So this is why they've been fairly popular. You can really calibrate them exactly in some sense. But one shortcoming is that once you do, once you have all these European prices, that pins down your local volatility model, and you don't have any degrees of freedom left to adapt the model to account for different kinds of exotic risks. So this is one weakness here. If you want to calibrate to both, European option prices and certain exotics that you're interested in, you can't really do so because the European options pin down already what your local vol model needs to be. Okay, so this is one reason that stochastic volatility models become popular. So a stochastic volatility model basically just replaces this local vol function with some generic stochastic process. So this ZT is an auxiliary stochastic process, often itself driven by some Ito dynamics. But in general, this could be more recent literature has taken this to be driven by a fractional Brownian motion. There are all kinds of things you can do here. And these are very flexible models, but they're hard to calibrate. There's no Dupier's formula, right? Your given stochastic vol model, your favorite stochastic vol model, maybe Heston, will have a finite collection of parameters that you can calibrate with, but you're not going to be able to fit exactly like you can using a local vol model. And this finally brings us to the subject of this talk, which are called stochastic local volatility models, or local stochastic, which basically just smushes these two ideas together. So you take your stock price to have a stochastic term, ZT, and also a local term, The idea being that you will use the stochastic part as you like to normally in a stochastic vol model, but by putting back a local vol term, hopefully you can calibrate things more easily to the given European data. So this is, I'll refer you to the books and papers of Julien Guyon and Pierre-Henri Labordère, who have written a good deal on these kinds of models and how to calibrate them. So the idea is that we can calibrate to, let's say, the local vol model from above. So this one I wrote up here, let's say. So suppose we use Dupier's formula. We look at our European prices on the market. We use Dupier's formula. We determine our favorite local volatility model, sigma hat. Now, if we want our local stochastic volatility model to match the European prices, then we want to have ST equal in distribution to S hat T for all, let's say, T positive, right? So if we want to use this model and we want it to be exactly calibrated to the same European prices that we calibrated our local volatility model to, then that means we want all of the time T marginals to agree. And for this to work, we basically need this Markovian projection to match up in the following sense. If we take this sigma hat T of ST should agree with the square root of the expectation of this volatility squared. So if we square this volatility and take the conditional expectation, because I have ST on both sides, so I can drop that one out. So if this identity holds true, then according to this Markovian projection theorem, these time marginals will all agree, right? We condition the square of this volatility, we get back the one from the local vol model. So they have the same time marginals according to this Markovian projection theorem. But now if we just rearrange this equation, then to have, so that we know sigma hat here, we don't yet know sigma. We're trying to figure out a calibration formula for sigma. If we rearrange this just by pulling the sigma outside of the conditioning, we deduce that we must have sigma of TST equal to sigma hat divided by the square root of this conditional expectation of ZT squared. And if we go back to our original equation with this and plug this in for sigma, what we're really saying is that we need to solve this weird SDE. DST is, well, we just plug this in for sigma. We still have a ZT and an ST term there. So let's put DST over ST is ZT. And then right this way, sigma hat TST. And then ZT over conditional expectation of ZT squared given ST. Okay, so again, the idea is if we have our favorite stochastic vol model, ZT, our favorite stochastic volatility factor, and we want to use that in a model that's exactly calibrated to a given local volatility model, given by sigma hat, which you would get from Dupier's formula, then to do this, you need to solve this stochastic differential equation, which is very unusual, very non-standard, because of the appearance of the solution process itself as the thing you're conditioning on in this conditional expectation term. Okay, so this is the challenge here. So often, again, ZT will be given by its own auxiliary SDE, but in general, you might imagine ZT could be more complicated. But the point here is that this is the kind of the calibration equation for these local stochastic volatility models, and almost nothing is known about these SDEs, their solvability, existence, uniqueness, approximations. So again, these Gyöngy and Vlasov works develop what's called a particle method for simulating these things. It seems to work well in many cases. But again, they're upfront about the fact that actually for certain regimes of parameters, like for large sigmas, it seems to be unstable. The particle method does not seem to converge to anything, or it oscillates. So that this suggests that this well-posedness problem might actually hide some serious issues, right? There might be some actually strange things going on in these equations to understand here. So this particle method. Yes.
May I ask a question? So if you would do that in discrete time on a grid, can you just do a backward recursion? Would that work, or are there surprising difficulties coming up?
So in discrete time, things seem to work perfectly fine. If you kind of write down the natural Euler discretization of this, then you're only computing this conditional expectation at the previous point in your time grid, and there's no issues with solvability there. And if you make some modest assumptions of boundedness, like on sigma hat and z, then you can even pretty easily convince yourself that if you refine your Euler discretization, you're going to have a tight sequence of processes, so you can extract some limit in distribution along a subsequence, but it's very difficult to characterize these limit points in any way, because conditional expectations don't really behave well with respect to weak convergence. So there's no problem with the Euler scheme, but there is a problem with the Euler scheme converging. It's really not clear what's happening there. Yeah, good question.
Thank you.
Yeah, so maybe if I have time at the end, I'll also mention there's an interesting counterexample that Scott Robertson showed me, which says that if you replace this conditioning on ST with conditioning on the past up to time t, then there can be no solution of this equation, at least if you assume z and w to be independent. There can be no solution. Actually, the same remains true if you only condition on an infinitesimal past of the process at time t. Now, we will show that there are solutions if you just condition on time t, but there's this interesting counterexample from Scott that shows if you condition on st in any infinitesimal part of the history of s before time t, there's no solution anymore. So this is a very, very delicate kind of equation, it seems. And the only paper I know really with any prior results on this is a paper from Jordan and Zhou, which appeared several years before, but the published version is from 2019. And again, I'll mention the Gyöngy and Henri Labordaire work, which interprets this as a McKean Vlasov equation. So if you have an auxiliary SDE for the process Z, then this kind of becomes a McKean Vlasov equation. So if Z itself solves some stochastic differential equation, then you can think of this as an SDE where the coefficients depend on the joint law of the solution, ST, ZT. But now the dependence on this joint law is quite bad. It depends on the joint law through a conditional distribution. And this is not going to fit into any of the standard theory for McKean Vlasov equations. The conditional measure is not weakly continuous. This operation of conditioning a measure is really not continuous in any nice sense, and that's prohibited any real adaptation so far of kind of standard McKean Vlasov theory. Nonetheless, this particle method from Gyöngy and Henri Labordaire says, like, okay, let's just pretend things are kind of well posed and go with the usual n-particle approximation of this McKean Vlasov equation, introduce a mollification to handle the local nature of this conditioning, and it seems to behave well again in many cases, but not in others. So there really is something strange going on with these equations, and there's not much known about them. This Jordan-Zhou paper shows that if the process ZT is a finite state Markov process, independent of W, then under pretty modest assumptions, you can construct, you have existence of a solution. There was a previous paper from Abergel and Taché from about 2011, which has a very, very local in time kind of existence theorem under very unverifiable smallness conditions. So I won't say much about that one, but I hope the essential setup is clear here, and the version of this SDE is what are the main results I'll present are about. So again, feel free to interrupt me if there are any questions here about the motivation or the form of this equation. Otherwise, let me discuss the setup we work with and our new results. So I'm going to switch notation from SZ to XY here. And X is going to be, this is our stock price. Y is our stochastic vol factor. So Y is itself going to satisfy some SDE driven by some Brownian motion, which I'm going to assume is independent of the Brownian motion driving the X equation. And X is going to satisfy some SDE, but with this kind of mimicking term, this ratio that's designed precisely so that when you take the conditional expectation, as you would in the Markovian projection theorem, it vanishes. And we'll also put a term like this in the drift, because these things do show up in practice. I should mention these models really are something of an industry standard from what I hear. Bank of America apparently has a huge FX platform just built on these models, even though we have no theoretical guarantees about them. And sometimes these drift terms do show up in this form there as well. So I'll put assumptions on these factors, these functions in a moment, but first to just write down the equation. This is the form we're looking at here. And again, the idea is that a solution should satisfy, or I'll say will satisfy, I'll be more confident about this, any solution of this two-dimensional SDE system will agree in its time t x marginals with this auxiliary process x hat, which is given by the same equation as x, but just with these ratios removed. So we have v1 x hat and sigma 1 x hat.
Then may I ask a question?
Please.
So is there any importance that this is autonomous, or is it just for simplicity for the presentation here?
Good question. So it will be very important to us because it turns out our results are for existence and uniqueness of stationary solutions. Mm-hmm. So we only work with invariant measures for these equations. We don't solve the time-dependent case. This seems more difficult, and this technique we found only really works in the stationary setting. Yeah. So I should comment also that this independence of the W and B is somehow less than ideal. In many cases, in stochastic volatility models, we like to correlate the Brownian motions that drive the asset price and the stochastic vol factor. So this is an unfortunate limitation, but we do need it for our technique to work out. So to the statement here, let me mention that this relates to this family of problems, this broad family of problems in math finance in the past couple decades of you might vaguely describe as problems where you know marginals of things and you're somehow I mean, maybe this is even too vague to try to categorize, but this somehow connects to these problems where you're given the marginals. So in this case, we know the x hat process and the y process. We know they're marginals, and we're trying to couple them in a certain way so that this two-dimensional SDE is valid. But any solution of this two-dimensional SDE must match the marginals of this autonomous equation for y, which doesn't depend on x, and also this equation for x hat here. So it's very tempting, and I explored this direction briefly, it's very tempting to imagine there's some kind of optimality principle, optimal transport behind the scenes here, some sort of cost function maybe for which the coupling that optimizes this problem would also solve this SDE, that there would be some kind of optimality condition governing this particular kind of coupling. Now, I could, of course, mention there are all kinds of ways you could couple these two processes to take your Markovian SDE and build more randomness into it, but preserving its time marginals. This particular way really insists on a particular sort of shape for this extra stochasticity that you're injecting. Right? There's a huge, an infinite family of processes that agree with the time marginals of this x hat. But in practice, you want to build one kind of that's related to your given stochastic vol process. So there is a connection here with these kind of marginal problems that Mr. Hobson, of course, is an expert on here. But I haven't really found that perspective to be useful yet, but that doesn't mean it's not. Okay, so let me give you our main theorem here. So first, some assumptions. Since let me mention right up front that our theorem is about stationary solutions. So if you give me your favorite initial joint distribution of x0, y0, then I have no idea if there's a solution or not from that initial distribution. But I can find an initial distribution for which the SDE is solvable and stays in that same joint distribution over time. So we need to assume, first of all, that the marginal equations, the y equation and the x hat equation, are nice enough that there exists a stationary solution for each of those individually. So a natural assumption would be a dissipativity kind of assumption for these drifts. And a linear growth assumption should come as no surprise as well. So these C1, C2, C3 are constants. We're also going to assume some boundedness. So the sigmas and these mimicking functions, the h and f, are bounded above and below away from 0. And lastly, some derivatives are bounded as well. So anything appearing in a volatility term should have a bounded derivative. And this will come from some use of some regularity results for elliptic PDEs. So under these assumptions, our first result is that there exists a stationary solution. It's a strong solution. So by stationary, of course, I mean that xt, yt in joint distribution is equal to x0, y0 for all t. And second, this is kind of an intriguing case if h and f squared happen to agree. So h is the drift term here, f is the volatility term. If h and f squared are equal, then the solution is unique in law. And in fact, this unique solution is the independent one. So xt is independent of yt. The for all t is redundant because the joint distribution is the same at each time. Okay, so this case is kind of surprising that the unique solution here is the independent solution where x and y are independent. This probably comes as a surprise at first. So I want to, for the rest of the talk, I'll start by explaining the idea behind this interesting case, and then as time permits, I'll give some ideas behind the proof of this first statement here. But I hope if there are any questions or clarifications needed about the statement of the theorem, again, feel free to interrupt me. Otherwise, I'll comment a bit more on this second point here. So I should mention first that x and y are absolutely not independent as processes. And this should be clear just from the form of the equation. The dynamics for y show up in the dynamics for x. So they couldn't, the evolution of x infinitesimally clearly depends on y, so there's no hope they'll be independent at the process level. But at any fixed point in time, xt and yt do happen to be independent. Now, the intuition for this, so let me give some ideas behind too. The intuition for this comes as follows. So suppose, let's say z satisfies, not right quite as much, if z is a stationary solution of some SDE, and if we look at a different SDE, where we take some constant c, and we multiply c squared in front of the drift b, just c in front of the volatility, these two equations have the same stationary, the same invariant measure. And the reason is simply that this c, multiplication by c, simply amounts to a time change. We're just changing from t to ct, our clock here. Okay, so if you perform a time change, the dynamics change in a way, but the stationary solution won't change because we're just going to, reach it faster if c is large, for instance. So this multiplication by a constant here just amounts to a time change. If we look back at our equation, we have h here and f, and I'm claiming that h is f squared. So in a way, so we have we have f squared here of yt and f of yt showing up in the equation for x. So in a sense, the idea of this 2 here is that this time change idea, the idea that time change does not change your invariant measure, somehow remains true if we perform a time change, a stochastic time change coming from an independent process, yt. So that's not obvious at all at first that a stochastic time change like this would, again, keep the invariant measure intact, but it turns out to indeed be the case. You can give a probabilistic argument for this. I find a kind of PDE argument to be a bit more transparent here. So let's suppose, I'll give you the PDE proof sketch for the second claim here. So let's suppose M1 and M2 are the stationary solutions, the stationary laws for the x hat equation and the y equation. So x hat has drift B1, volatility sigma 1, y has drift B2, volatility sigma 2. So in PDE form, we have a weak solution of this, well, there's an ordinary differential equation governing this invariant measure. These are one-dimensional processes. And these are stationary, so we have a 0 instead of a time derivative on the left-hand side here, and this is just the stationary Fokker-Planck equation for the SDE here. So for I equals 1, 2, in at least an integrated, at least in a weak sense, this M1 and M2, these laws should satisfy these ordinary differential equations. So we have a first derivative on minus the drift, second derivative on the volatility squared. Now, if you take the first equation and write it a different way, we have b1 of x times m1 of x, and we have sigma 1 squared of x times m1 of x. And here we have an x derivative, and here we have a second x derivative. And similarly, we have an equation for y, which we can write in a different way. I'm leaving some space so I can add some more things into this equation in a moment. The idea is we're just going to multiply in both of these equations by some common factors to make the product measure appear. And then we're going to add them together, and we'll find that the product measure satisfies the right two-dimensional PDE for stationary measures for x and y. So we'll let first c be 1 over the expectation of f squared of y with respect to the stationary law m2. And p is going to be our product measure, m1 of x, m2 of y. So these stationary equations for m1 and m2 just rewrite as follows. We write them in terms of x and y. And then in this first equation, I can multiply on both sides by something that just depends on y. So I can multiply here by c times f squared of y, and also m2 of y. And that isn't affected by the x derivative. And I need to multiply by the same thing in the second term here. And then likewise in the second equation, I can multiply through by m1 of x, since this is not affected by the y derivatives. Okay, and then the m1, m2 becomes a p, and we find by adding these equations that p solves this equation here. We have c f squared of y, p of xy. We have c f squared of y, p of xy. In the second derivative term, there should have been an x here. We have p of xy times b2 of y in the y derivative, and the p of xy sigma 2 squared in the second y derivative. And this is exactly the stationary PDE corresponding to this SDE here, where we have b1 of xt and then f squared of yt divided by its expectation, right? C was 1 over the expectation of f squared. And then likewise in the volatility term, we have the square root of this same thing. And then the same equation for yt as usual. Okay, so this shows, okay, if we start with the marginals m1 and m2, the marginal stationary laws, we multiply them together to get p. This is the independent distribution for x and y. Then this PDE argument shows that p of xy, this product measure, solves the right PDE associated with this two-dimensional SDE. And note that these conditional expectation terms are just expectations when these are independent random variables here. Okay, so then again, using this result of Figali or Trevisan that I mentioned at the beginning, you can make this rigorous, saying that if you have a solution of the right PDE, then that gives you a solution of the SDE, even if you don't know anything about smoothness or regularity or anything of the sort. So this stochastic time change still works here. This PDE argument, I hope, can convince you of that. There is a time change argument as well that you can make work, but it's a bit harder to make sense of the stochasticity showing up there. So I might mention also that this f squared, this h equals f squared term does show up precisely if you take, say, some asset price zt, or st, sorry, you have some process of this form, which is like a geometric Brownian motion. and you take x to be log of s. So if you start with a martingale with a term like this, and you take the log of this price, then x will satisfy an equation like this with this condition satisfied, h equals f squared. You'll get the square of this term showing up in your drift. So this special case is quite special when the h and the f squared line up, but it is actually reasonable from an applied point of view here as well. Although stationarity is not quite as reasonable when you're looking at a martingale here. So there's you know, the stationarity is a bit of a shortcoming here from the application perspective, but you can, it's a start nonetheless, and you can imagine kind of tweaking your coefficients at infinity to make them amenable to the stationarity conditions. But then you might need to recalibrate over time. So anyway, I don't want to go too much into that, but this is the idea behind this second case, this case where we do have uniqueness. And in this first case, where h and f squared can be different, we only claim existence. Now I think I just have a few minutes left. So maybe I'll mention, I'll just give the first ideas of the proof of existence here. This again follows PDE techniques. I normally prefer stochastic or probabilistic methods when I can, but we didn't find any successes there, and the PDE is what ended up working here. So the idea, well, if we write down the PDE for the joint density P of xy. So just suppose there's a solution that has a joint density. We can write down what the stationary Fokker-Planck equation looks like, and it will involve all these terms that I like to denote as follows. So this g sub psi of P of x is basically going to be a reciprocal of the conditional expectation, this term that shows up repeatedly in our equation. So think of this as 1 over expectation psi of y given x, when xy has the distribution p. Now our PDE here becomes, again, we have a 0, not a time derivative because we're stationary. The drift for x is v1 of x, h of y times this gh p of x, and then p of xy. The drift of y, we have a b2 of y, and that's all. And then in the volatility of x, we have, again, a conditional expectation term. So we have an f squared y and a g f squared p of x. And then in the y term, the y volatility, we just have a sigma 2 squared. And really, we write this PDE in weak or integrated form. We multiply by a test function, integrate both sides to take the derivatives away from p. But nonetheless, this is the better shorthand for the PDE we're studying. And the way we study this is kind of common in these McKean Vlasov type equations. The way we study this is by freezing the nonlinear term and constructing from it a fixed point map. So the difficulty with this PDE is, of course, these two terms that involve the conditional expectations. So this makes the equation nonlinear with respect to p, and also non-local in the sense that we're integrating at least in one of the variables. So it's some kind of mix between local and non-local because we're only integrating over the y variable, not the x variable. Nonetheless, the idea is that we fix, let's say, p hat to start with. We fix some p hat, some density function p hat, and then we solve the linear PDE that we get by plugging in p hat into these nonlinear terms. And the goal is to match the P that we get to the P hat we started from. So this is the fixed point map we want to work with. Our assumptions on the coefficients are nice enough that for a given P hat, there's a unique stationary solution, P, associated with this linear equation. And then it's just a matter of trying to prove existence of a fixed point. To prove existence of a fixed point, we ultimately use Schauder's fixed point theorem. Contractions seem kind of impossible to come by here, but we are able to get enough compactness and continuity to use Schauder's theorem, right? To use Schauder's theorem, you need to find a compact convex set in some reasonable vector space so that this map from P hat to P preserves this set K and is continuous. And this is not so easy to do here. To find compactness, we need some kind of PDE estimate, some kind of a priori estimates. And this is where the real challenge here lies. This is difficult because the action is in the volatility term. If f were 0, if this function f were 0, meaning the only action, the only conditional expectation term was in the drift of x instead of the volatility, this would be much easier. But because the action is in the volatility term, things become quite tricky, and they become tricky because the smoothness of P depends on the smoothness of this volatility coefficient. So the usual kind of estimates you'll find on, let's say, the derivative, like an H1 norm of P, or rather the square root of P usually, but details aside, the estimates on the first derivative of P that you'll find in the literature depend on like an L2 norm of the drift, but also an L2 norm involving the derivatives of the volatility coefficients. And the derivative of this conditional expectation term with respect to x is not a very nice thing to work with. Its smoothness depends on the smoothness of P, and we end up with something kind of circular here. What we would really like is some smoothness estimate for P that does not depend on as much smoothness as P hat. We want this map from P hat to P to somehow improve our smoothness. And this simply does not work for this equation as it's written, but the key idea that made this work is a transformation, a change of variables of sorts, where we write an equation instead for what we call Q, and this function Q we get by tilting the conditional measure of y given x. So I'm running low on time, so I won't say much more about this. But that when you do change variables here, this transformation from P to Q turns out to be invertible. You can map back from Q to P. Again, F is bounded from above and below, so you can show that this transformation is bijection on the space of probability densities. And the equation for Q is actually in many ways even more nasty than the equation for P up here. But the key point is that the equation for Q does not have this term, this conditional expectation term, in the x derivative part, in the x volatility. It has this term instead over in the y derivative part. And this may not seem like an improvement, but it turns out when you look at the precise estimates in the PDE literature, to get smoothness for P, this will depend on the x derivative of the x volatility coefficient and the y derivative of the y volatility coefficient. So you don't need all of the cross derivatives. You don't need the y derivative of x's volatility or vice versa. So this transformation from P to Q puts the bad term over in a place where it doesn't hurt us as much. And then we can get some a priori smoothness for the Q solution independently of the nonlinearity part that we freeze. And this enables some kind of smoothness improving property of this fixed point map. And from there we can get compactness and continuity and ultimately complete the proof. So that's a bit sketchy. The ultimate ideas we use, though, are due to the smoothness estimates come from some very nice recent work of Bogachev, Krylov, Rockner, and some other co-authors on other related papers. These guys have really done a great job in the past decade of ironing out the kind of precise regularity properties of SDEs, particularly when there's a non-constant diffusion coefficient. So this is some really nice work to get to know that really saved the day here after we found this appropriate transformation. So yeah, again, let me just close by reiterating that you know, I see this as kind of a modest result in the sense that there are many restrictions we're working with here, but this is really a wide open problem here to understand anything about existence and uniqueness of these bizarre SDEs involving this conditional expectation term. It would be great also to have a rigorous support for this particle method that seems to be widely used in practice and is written about by Gyöngy and Henri Labordaire. So if you're not, you know, totally convinced by the stationary solutions, I hope you're at least curious about this problem, which I find to be fascinating, and there's still a lot of work to be done on this thing. So with that, let me thank you for your time and attention, and I'm happy to stick around to answer any questions.
Right. Okay. Thank you very much, Dan. So are there any questions? Martin, I guess.
Yeah, thanks a lot for this fascinating talk, and this proof looks also very fascinating. So just to understand, if there wouldn't be, so the volatility would be 1, say, so constant, would you then get uniqueness, or would it still not, you could still no contraction argument, would still not work?
You mean if this term was not here in the...
Yeah.
That's a good question. I haven't thought about this. I still suspect the contraction would be hard to come by. But it does seem existence should be much easier, and yeah, even in the time-dependent case, their existence, I'm guessing, is doable, but uniqueness could still be pretty difficult, I imagine. In any case, the real financial application has it in the place you don't want it, so we didn't spend too much time thinking about that case.
And does this work for high dimensional? So only works for the one-dimensional case?
Good question. Yeah, so we did think a little bit about the higher dimensional case, but there are 2 things I'll say about that. First is that it's a bit less natural to set up a multi-dimensional version. I guess because you kind of need to decide what you're calibrating precisely. So if X is multi-dimensional, then this conditional expectation term given X would make sense if you have access to somehow all European options written jointly on the whole vector of asset prices. So, you know, just all the call options on each individual asset would only give you the individual marginals, X1T, X2T, etc. So that wouldn't pin down the joint distribution. So it wouldn't make sense then to condition on XT unless you also had access to functions of all of them. So it's not clear precisely what the natural formulation would be in multiple dimensions. But ignoring that and looking at this equation on its own and allowing X and Y to be multidimensional, there's, I believe, one point in our proof where we use a Sobolev embedding that's specific to dimension 2. And I think that step would break down here if you go to higher dimension. You may need to be more careful about the PDE estimates, but I would need to check to confirm that. Otherwise, the strategy should work for this equation.
I see.
Might be a problem with the embedding there.
Okay, thank you. So are there more questions or comments? Yeah, so I have another question. Probably it's not that related. So give me a feeling. So this is a kind of a connection between general process and the Markovian case, right? I think you must know this functional Ito's formula, right? So you can also convert this say path dependent case to kind of a Markovian case, but sit on infinite dimensional space. So do you think there's any connection between these two, or is it totally irrelevant?
Yeah, this I'm not sure about off the top of my head.
Because kind of you also kind of do a projection, so you reduce this general Ito process to a Markovian process, right?
Right. So there are variants of this Markovian projection.
Yeah.
The Brunick-Shreve paper kind of beautifully collects them all together and proves them all at once in a way. But so for instance, if here you condition on the path up to time t instead of on the value at time t, then this gives you path-dependent functions. Sigma hat. And then you can solve the theorem the rest of the theorem remains true. You can find a weak solution of this SDE, which now becomes path dependent, but there's no extra randomness depending on, say, omega. And this weak solution now agrees in law as a process, not just with the time t marginal. So there are other versions where you condition, like say on xt and its running maximum in order to preserve the joint law of that object. So there are all kinds of variants like that could lead you to different sorts of SDEs where you're calibrating to different kinds of information, different kinds of
objects. I see.
And we haven't explored beyond this Markovian case yet, but this is an interesting point that you could imagine. Projecting in different ways and getting different kinds of equations.
Okay. Good. Thanks. So, any more questions? Motorcycle. So if no more questions, so let's thank Dan again for the very interesting talk. And you